Good morning, good afternoon, everyone, and thanks for your introduction. Today, I'm going to present preliminary numerical results on the structural dynamic behavior or reinforced concrete beam structure affected by damage phenomena. The creators of this work are Professor Greco and Lonetti and Dr. Pranno and Maio from University of Calabria. The presentation will be structured as follows. First, an introduction about motivation and objective of this work, and a brief explanation of the structural health monitoring context. Then, an illustration of the theoretical background used for the model. After that, I will show the characteristics of the numerical model, and in the end, I will present preliminary results derived from static and dynamic analysis. In recent years, interest has been growing in the field of structural monitoring of existing structures with the aim of preventing sudden collapses that would entail risks in terms of loss of life and not insignificant economic repercussions. The research focuses on reinforced concrete bridges since it is the type widely used in road and rail networks. Moreover, concrete is subjected to progressive deterioration due to damage phenomena induced by natural and anthropogenic agents. An important objective of this work concerns the analysis of the structural behavior of reinforced concrete beam affected by damage phenomena, with the aim of identifying the presence, the location, and the extent of the damage itself through non-destructive monitoring strategies. To achieve this objective, it will be necessary to develop an advanced finite element model capable of reproducing the effect of damage phenomena on the dynamic properties of bridge structures. So, in the cases of damage detection methods, vibration-based techniques are based on the concept that the damage will alter the dynamic properties of the structures, and it's possible to detect the occurrence of damage phenomena by measuring the dynamic structural response. To the vibration-based methods belong the data-based and the model-based techniques. The first one is based on statistical model extracted from the time history responses. And the second one is based on a physical model of the monitored structure, for instance, on a finite element model. Damage identification can be conducted through an inverse problem or a forward problem that involves a numerical model. The concept at the base of the model-based techniques is summarized in this slide, and they are based on the comparison between the dynamic response of the structural system predicted by a mathematical model on the vibration and the vibration response determined experimentally on the real structure for non-ambient excitations or forced excitations. Within the structural health monitoring procedures based on the coupling between numerical models and experimental data, the proposed model method has been implemented to investigate the load-induced degradation of vibration characteristics in reinforced concrete beam. In order to take into account all the complex nonlinear phenomena induced by the applied load, including concrete cracking and rebar yielding, two different models have been incorporated into a 2D finite element framework. The first one is used to reproduce the structural behavior of a damaged reinforced concrete beam. And it's called the coupled damage plasticity model, proposed by Peter Grassel in 2013 and co-authors. The general constitutive equations are based on the concept of the damaged and undamaged stress tensor. The first is used in the weak formulation, while the second describes the behavior of the intact material. Two damaged variables are introduced for the tensile and compressive state and provide a weakening of the material stiffness by varying from 0 for an undamaged state to 1 for a fully damaged state. The plasticity model is based on the effective stress and can be summarized by the evolution equations for the plastic strain and the hardening variable, together with the Cantaker loading conditions. The adopted yield function is a generalization of the William-Warren criterion, which introduces two-dimensionless functions able to control the evolution of the size and shape of the yield function. Of the yield function, yes. On the other hand, the damage model is described by the damage loading functions, the Cantaker conditions, and the evolution laws of the damage variables for tension and compression state in the framework of isotropic damage mechanics. The equivalent strain is the same for both tension and compression state, and it's derived from the plastic yield equation imposed equal to 0. The softening behavior in tension and compressive state follows, respectively, a bilinear and exponential evolution law. Okay. The second model implemented is called the embedded truss model and allows to capture the interaction between concrete and steel bars. The numerical model was implemented using the software COMSOL multiphysics. The present numerical simulations involve a 4-point bending test analyzed by Ahmad and co-authors in 2015. We can see the details of the geometry configuration, boundary conditions, and material properties of the structure analyzed. Moreover, it showed the unstructured mesh composed of 3 node triangular elements arranged in a Delaunay tessellation used to discretize the bulk phase, and 1D 2-node elements used for longitudinal bars and shear stirrups. Preliminary, the proposed model has been validated by means of the 4-point bending test performed on a reinforced concrete beam, evaluating the ultimate load and defining 9 loading equilibrium paths, comparing results with experimental and numerical data. The load versus midspan deflection curves highlights a good agreement between the experimental and numerical loading curves. The loading path exhibit residual plastic deformation. For high value of damage from L6 to L9 level, 2 different slopes have been observed. They are related to the combined effect of the concrete plasticity and the partial contact between crack faces, which cannot completely close due to the presence of aggregates and the sliding phenomena occurring at the concrete rebar interface. Subsequently to the static analysis, a linearized eigenvalue problem of the structure has been solved by performing the analysis of small amplitude free oscillations superimposed on the damage scenarios previously obtained at the final points of each unloading path. The dynamic response performed at different load levels shows a reduction of the natural frequencies as the load level increases, mainly induced by the evolution of damage phenomena in the tested structure. As we can see, the degradation of the frequencies of the proposed model at different load levels doesn't follow the frequency behavior of the control beam test results. And this is due to the nonlinearities present in a crack vibrating beam, so due to the opening and closing of the cracks. To take into account this nonlinear behavior of the beam, in the literature, it's proposed an effective natural frequency calculated as a combination of the natural frequency for crack open configuration and natural frequency for crack closed configuration. This is called bilinear frequency, and it was proposed by Chatty and co-authors in 1997. But also the degradation of this bilinear frequency doesn't show a good agreement with the experimental results. This is because the bilinear frequency formula is derived for a single crack. Instead, in this model, there are diffuse multiple cracks. So, in order to reproduce the dynamic experimental behavior of the cracked beam and to overcome the problems caused by the nonlinearities, it's proposed a linear combination of the frequency at the unloading phase, that is the crack open configuration, and the frequency at the unloading phase, that is the crack closed or partially closed configuration, for different load levels. The parameter A and B were determined using as objective function the mean square error between the optimized frequencies and the numerical experimental frequencies. And the ordinary least squared is used as optimization function to minimize the mean squared error. These parameters were evaluated for the first mode and then applied to all of the modes considered. The common dynamic damage indicators available in technical literature have been employed to assess their capability in damage detection for strengthened structures. Two different indicators have been adopted. The first one is the modal curvature. For the modal curvature, we can see that in the early load levels, the constant bending zone is most affected by the slope changes of the modal curvature. Subsequently, significant peaks in the curvatures are detected in the shear zones of the beam. However, it can be deduced that to detect adequate diffuse damage phenomena through the modal curvature method, more than one vibration mode must be analyzed. So to overcome this issue, the second indicator, the curvature damage factor, has been analyzed because it's not focused on the modal curvature of the single vibration mode, but it's based on the summation over all investigated modal shapes of the absolute differences between the modal curvature obtained at the generic coordinate for undamaged state and the damaged state. After the earlier load levels, the curvature damage factor shows local minimum and maximum points distributed along the entire span of the beam, and it individuates the position of the cracks. In conclusion, in this work, a numerical investigation of the dynamic characteristic degradation induced by damage phenomena in reinforced concrete structures has been presented. The constitutive model, coupled damage plasticity model used, is able to reproduce the real crack pattern of reinforced concrete structures subjected to cyclic loading conditions. Moreover, the proposed optimization frequency approach leads to more accurate results in the case of diffuse multiple cracks, which better represents the real damage scenario of reinforced concrete beams. The advantage of this approach is that only two parameters must be detected. Sorry, I have a little problem. Okay, must be calibrated, detected. In the end, the common dynamic damage indicators based on the modal curvature are employed to identify the location and the extension of the damage. They provide accurate detection of the crack pattern, even for the low load levels. Future developments of this work may be the application on different structural examples and configurations to establish a broader correlation between calibrated parameters and the type of structural problem analyzed.